Good evening, everyone. I am April Ann Perugasa, and I am going to report Chapter 12 of Bridge Engineering Structural Modeling. This Chapter 12 tackles about introduction, theoretical background, modeling, available computer programs, selection of modeling methodology, geometry, material and section properties, boundary conditions, and loads, then summary and references. Introduction. Structural system can in most cases become too complex to be designed based solely on empirical data or experience. A more rational procedure using a mathematical simulation of a structure is needed to understand the performance of the structure under various loading. The response of the structure will become even more complex if the loading is time dependent. An example of a time-dependent loading is ground motion excitation, during which the structure can be subjected to strong ground shaking and high accelerations in both horizontal and vertical directions. Another source of complexity to the structural system, for example, is when the interaction of structure with soil, foundation system or embedded structures, or with fluid, tanks or floating structures becomes important. If the design criteria allows for limited and controlled damage, or when passive energy dissipation systems, isolation, or sliding systems are used in the structure, the nonlinear behavior of the elements need to be included, which in turn requires more attention to ensure that the mathematical model provide a reliable representation of the physical system. The purpose of this chapter is to present basic modeling principles and suggest some guidelines and consideration that should be taken into account during the structural modeling process. In addition, in addition, some examples of numerical characterization of selected bridge structures and their components are provided. The outline of this chapter follows the basic modeling process. First, the selection of modeling methodology is discussed, followed by the description of the structural geometry, definitions of the material and section properties of the components comprising the structure, the description of the boundary conditions and loads acting on the structure. 12.2 Theoretical Background. Typically, during the analytical phase of any bridge design, finite element or FE procedures and programs are used to evaluate the structural integrity of the bridge system. Most structural analysis programs employ sound, well-established FE methodologies and algorithms to solve the analytical problem. Other important issues to consider include numerical solution techniques used in matrix operation, computer numerical precision limitations, and solution method used in a given analysis. There are many solution algorithms that employ direct or iterative methods and sparse solver technology for solving the same basic problems. However, selecting these solution methods efficiently requires the user to understand the best condition in which to apply each method and the basis or assumptions involved with each method. Understanding the solution parameters such as tolerances or iterative methods and how they can affect the accuracy of a solution are also important, especially during the nonlinear analysis process. The first attempt to automate the structural analysis was to code the technique that were being implemented in hand calculations, such as moment distribution procedure. It did not take long for engineers to realize that the methods that are efficient for hand calculations are not necessarily the best for computer analysis. Therefore, stiffness matrix approach using the virtual displacement procedure that involves assembling the stiffness of each element into a global stiffness matrix was adapted for numerical analysis. Although it is not practical for hand calculations, this procedure can be automated rather efficiently before engaging in the modeling of the physical system of interest. It is essential that the engineer identifies the objectives of the analysis. These objectives can be translated into set of the parameters or unknowns that are computed as a part of the analysis execution. The basic parameters include only unknown degrees of freedom of the mathematical system. The mathematical process for this procedure is summarized below. So first is to analyze the structure. The first step is to select unknown global degrees of freedom or DOF. These are the basic unknowns, and once they are computed, the other unknowns, such as element forces and element deformation, can be obtained easily. Therefore, it is necessary to establish the relationship between displacement and element deformations. 2. Therefore, the next step is to formulate a relation between global DOF and element deformations. It is important to note that deformations do not contain rigid body motion, whereas displacements often do. These are kinematics equations that relate the displacement to element deformations. This relation can be linear or nonlinear. For large displacements, the relation between the two is nonlinear. In some structure, a linear relation between deformations and displacement may provide sufficient accuracy, whereas in other structure, such as suspension bridges, the relation between deformations and displacement is nonlinear. 3. Since the element of deformation are related to the global displacement DOF through kinematics, the formulation of action deformation element for each element will relate the element forces to element deformations and global DOF. The stress-strain relation for each element defines the action deformation. This requires that the sectional and material properties of the element be defined. The relation between element force and its deformation can be linear or nonlinear. 4. Having a clear definition of the relation between element forces and element deformations, they can be easily related to the external forces using virtual displacement principle. For structures with large displacement, the equations of equilibrium should be solved in the deformed configuration. This means that the stiffness for each element and the structural stiffness should be updated as the structure deforms. Finally, the equations of equilibrium can be solved and the unknown global displacement can be obtained. 3. Sources of nonlinear in any structural engineering analysis as follows. So we have 3. First is the kinematics, a relation between deformation and displacement of geometry. Then 2 is the materials. 3 is the equations of equilibrium. Equations of equilibrium can be solved in the deformed or the undeformed shape. So there are 2 methods that incorporate the large displacement in the analysis. The first method is an approximate method. In this method, the stiffness matrix is assembled once in the undeformed configuration with no iteration. The displacement and deformations and element forces are computed in the undeformed geometry. Therefore, the stiffness matrix is first order. The geometric stiffness is computed based on the computed forces and based on the undeformed configuration. Therefore, it is an approximate correction only. The displacement, deformation, and element forces will be computed with the modified stiffness in the undeformed geometry. Note that there is only one cycle to compute the geometric stiffness. There is no iteration nor any consideration for the deformed configuration. Therefore, this method is very simple to be added to linear elastic programs. In this method, a linear shape function is assumed and equations of equilibrium are solved in the undeformed configurations. This method is sometimes called second-order correction analysis. Note that in this method, the equations of equilibrium will not be satisfied in the deformed configuration. So the other method is true large displacement analysis. In this method, the equation of equilibrium are directly solved in the deformed configurations. In this case, even if there is no material nonlinearity, there is a need for iteration to obtain equilibrium. At each step, the geometry of the structure changes. Therefore, the relations between displacement and deformation change. Note that this relation is not linear. Therefore, at each step, a new stiffness matrix is generated based on the deformed configuration of the structure. Although nonlinear analysis can provide a more reliable response of the structure, more engineering judgment and validations are needed to ensure the validity of the analysis. So we have here the table 12.1, or the sources of nonlinearity. We have kinematics and action deformation, solve equation of equilibrium. So small displacement with linear elastic material properties. So kinematics, it's linear. Action deformation, it's linear. Solve equation of equilibrium in, it's the undeformed shape. The small displacement with nonlinear material properties, it is linear, nonlinear, and undeformed shape. Second order with linear elastic material properties, it is linear, then linear, and deformed shape. So second order with nonlinear material properties, it is linear and nonlinear and deformed shape. Large displacement with linear material properties, it is nonlinear. Then action deformation is linear, and then solve equation of equilibrium in is deformed shape. The last is large displacement with nonlinear material properties. Kinematics is nonlinear, action deformation is nonlinear, solve equation of equilibrium in is deformed shape. So 12.3. 12.3.1 available computer programs. So we have two types of computer programs, namely the general purpose linear and nonlinear FE computers programs, so such as ADINA, ANSYS, Nastran, and Abacus. These FA computer programs can be used for both simple modeling using beams and truss elements and continuum modeling. FA discretization or continuum monitor the state of stress and strain at each FA element. A large library of elements and material properties are available in these FA programs. Geometric nonlinearity can be explicitly included in the analysis with a true large displacement solution. So see table 12.1. These FA programs are more expensive and not developed for structural engineers only. Therefore, there is a need for a more modeling effort as well computer resources. As the computers become more powerful, the use of these FA programs becomes more reasonable. However, the engineers need to be trained with the nonlinear behavior and dynamic analysis to be able to develop a reliable model. So 2. Linear and nonlinear computer programs specifically developed for structural engineers such as GTS, TRUDL, STAAD 3, SAP 2000, and LARSA. These computer programs are written for structural engineering problems. Usually, the element and material libraries are limited to beams, truss, springs, and sometimes shell elements. Lump plasticity beams elements can have introduced in many computer programs with nonlinear capability. Approximate large displacement formulation, elastic second order. So let us see 12.1 table that is usually used in this computer programs where the stiffness matrix is modified with linearized geometric stiffness, whereas the equation of equilibrium are solved and checked on the undeformed geometry. 12.3.2 Selection of modeling methodology. Many factors contribute to the deformation of the modeling parameters. These factors should reflect issues such as the complexity of the structure under investigation, types of loads being examined, and most important, the information needed to be obtained from the analysis in the most efficient and design-friendly formats. This section presents the basic principle and considerations for structural modeling. It also provides example of modeling options for the various bridge structure types. Analysis process is not just an isolated activity, but it is computer experiments that disclose the physical characteristics of the structure. The first step is to understand the physics of the problem and be able to formulate the structure system. A conceptual model will need to be developed next to better understand structural behavior. Once a good understanding of a structural system is gained, model development should always be accompanied by the validation of the model. After validation of the model, the analysis and interpretation of the result will start. From this flowchart, it becomes very clear that there are several steps before and after the analysis that needs direct engineering judgment. For a reliable analysis and design, therefore, it is important to have a sound understanding and knowledge of structural mechanics, structural analysis, structural dynamics, nonlinear analysis, and nonlinear behavior of the structure even before performing any analysis. After analysis is complete, the engineer needs to be able to interpret and validate the reasons, results, and identify possible mistakes or misinterpretations of the intention of the modeling. So as you can see, figure 12.1, it is a design analysis process. Analysis process is a computer experiment. So it's not just analysis. So the first step is understanding underlying physics, developing conceptual model, then developing numerical model, then model validation, and analysis interpretation and design solution. The first step in achieving a reliable computer model is to define a proper set of material and soil properties based on published data and site investigations. In the second step, critical components are assembled and tested numerically where validation of these components' performance is considered important to the global model response. Post from solutions or available test data are used for these validations. The next step is the creation and numerical testing of subsystems such as the bridge towers, superstructure elements, or individual frames. Again, as in the previous step, simple procedures are used in parallel to validate computer models. A full bridge model consisting of the bridge subsystems is assembled and exercised. This final global model should include appropriate representation of construction sequence, soil and foundation boundary condition, structural component behavior, and connection details. And the last step, boundary condition definition and verification are essential part of the modeling procedure. So the assembled model will need to be subjected to applied load. The applied load can be static force or displacement or time-varying acceleration force or displacement. Following the analysis and after careful examination of the analytical results, the data is post-processed and the demand values are extracted. An important part of the overall analytical procedure is the determination of the capacities of the structural members. A combination of engineering calculations, computer analysis, and testing is utilized in order to develop a comprehensive set of component and system capacities. The evaluation of the structural integrity of the bridge structure, its components, and their connection are then conducted by comparing capacities with the demand calculated from the structural analysis. If the demand values meet the requirement of the design criteria, then the design can be finalized. Otherwise, the design needs to be adjusted and model needs to be updated for a new analysis. The entire process may be repeated to validate any modifications made, depending on the nature and significance of such modification. High-order FEs, such as three-dimensional solid elements or shell elements, can be used in modeling of a structure depending on the complexity of the structure under investigation and nature of the applied loads. More complex models, however, require a significant higher degree of engineering experience and expertise in the theory and application of the FA method. In the case of complex model, the engineer must determine the degree of refinement of the model. This determination is usually made based on the types of applied loads as well as the behavioral characteristics of the structure being represented by the FE model. It is important to note that the format of the result obtained from detailed models such as shell and 3D continuum models is quite different from the result obtained from beam or stick models. Stress and strains are obtained for each of the bridge components at a much more detailed level. Therefore, calculations of a total force applied to the superstructure, for example, becomes a more difficult, tedious task. However, evaluation of local component behavior such as cross frames, plate girder sections, or bridge deck sections can be accomplished directly from the analysis result of a detailed FA model. So figure 12.2, it is a FA model development process. First is material, definition and verification, then component, definition and verification, subsystem, global system, and then boundary condition. So figure 12.3 is a modeling analysis process. So we have model definition, then applied load, definition, then analysis or execution, our demand calculation. We also have capacity calculation, then evaluation of structural integrity of system and components. Then we have adjusted design, not okay. Finalized design, okay. So an example of low-order FE modeling is shown in figure 12.7. In this example, the engineer, based on the requirement of the design criteria and project needs, has decided to simplify the continuum with elements such as beam, truss, or springs. The results of analysis in this type of modeling are usually forces and moments. These results are normally associated with individual element coordinate system, thus simplifying the evaluations of these components. Normally, these forces resultants describe axial, shear, and tension and bending action at a given model location. Therefore, it is very important during the initial modeling stage to determine key locations of interest, so the model can be assembled such that important results can be obtained at these locations. Although it is convenient to use element coordinate system for the evaluation of the structural integrity of individual components, nodal results such as displacement and support reactions are usually generated for put out in the global coordinate systems. In many cases, during model development, high-order FEs can be mixed with low-order elements such as beams and truss elements. This hybrid modeling procedure can result in an efficient and yet accurate FE model. The simple model shown in figure 12.7 can be adjusted using hybrid modeling procedure as shown in figure 12.8 and 12.9 for a more complex structure with complicated geometric configuration. So as you can see, figure 12.4 is a typical FA model using high-order continuum elements. Then for 12.5, it is a typical FA model using high-order continuum elements as well. Figure 12.6 is a mesh refinement study. 12.7, it is a typical beam model. Figure 12.8 is a combination of high and low order finite element, a typical hybrid modeling. Figure 12.9 is a combination of high and low order finite element, typical hybrid modeling. So figure 12.10 is a steel plate girder bridge finite element method. 12.11 is a concrete box girder with 45 degrees skewed supports finite element method. Then figure 12.12 is a concrete box girder modeling example, deck elements not shown. The analyst must use engineering judgment to determine if the benefit of mesh refinement justify the cost. For example, for the convenience in design of bridge details such as reinforcement bar cutoff, pre-stressing cable layouts, and section changes. The bridge superstructure is usually modeled with a high degree of refinement in the dead and live load analysis to achieve a well-defined force distribution. The same refinement may not be necessary in a dynamic analysis. Quite often, coarser models are used in the dynamic analysis. These refinements are the minimum guidelines for discrete lump mass models in dynamic analysis to maintain a reasonable mass distribution during the numerical solution process. 13.3.3 Geometry. After selecting an appropriate modeling methodology, serious consideration must be given to proper representation of the bridge geometric characteristics. These geometric issues are directly related to the behavioral characteristics of the structural components as well as the overall global structure. The consideration must include not only the global geometry of the bridge structure, that is, horizontal alignment, vertical elevation, super elevation of the roadway, and severity of the support skews, but local geometric characterization for connection details of an individual bridge components as well. Such details include representations of connections regions such as column to cap beam, column to box girder, column to pile cap, cap beam to superstructure, cross frames to plate girder, gusset plates to adjacent structural elements, as well as various varying systems commonly used in the bridge engineering practice. Some examples of some modeling details are demonstrated in Figure 12.12 through 12.19. Specifically, the figure 12.12 demonstrates how a detailed model of a box girder bridge structure can be assembled via use of shell elements for girder webs and soffit, truss elements for post-tensioning tendons, 3D solid elements for internal diaphragms, and beam elements for columns. Figure 12.13 illustrates some details of the web, deck, and abutment modeling for the same bridge structure. Additionally, spring elements are used to represent abutment support condition for the vertical as well as back wall directions. So figure 12.13, it is a selected modeling design details. An example of a column and its connection to the superstructure is an explicit FE model is represented in the figure 12.14. So 12.14 is a bent region modeling detail. The three elements are used to represent the full length of the column. A set of rigid links connects the superstructure to each of the supporting columns. Figures 12.15 and 12.16. It is necessary to properly transmit bending action of these components, since the beam element or columns are characterized by 6 DOF per node, whereas 3D solids internal diaphragms carry only 3 DOF per node translations only. In this example, post-tensioning tendons are modeled explicitly via trussed elements with the proper drape shape, figure 12.16. This was done so that accurate post-tensioning load application was achieved and the effect of the skews were examined in details. Figure 12.15 is a column to superstructure connection modeling detail, and 12.16 is a post-tensioning tendons, diaphragms, and columns to diaphragm connection modeling examples. However, when beam models are used for the dynamics analysis, figure 12.7, special attention must be given to the beam column joint modeling for a box girder superstructure, since cap beams are monolithic to the superstructure. Considerations must be given to capture proper dynamic behavior of this detail through modification of the connection properties. It is common to increase the section properties of the cap beam embedded in the superstructure to simulate high stiffness of this connection. Figure 12.17 illustrates the plate girder modeling approach or a section of superstructure. Plate elements are used to model deck sections and girder webs, whereas beams are used to characterize flanks, hunches, cross frames members, as well as columns and cap beams. Figure 12.18. Proper offsets are used to locate the center lines of these components in their proper locations. So, figure 12.17 is a plate girder superstructure modeling example, while figure 12.18 is a plate girder band region modeling example. 13.3.4 Material and Section Properties. One of the most important aspects of capturing proper behavior of this structure is the determination of the material and section properties of its components. The Roark's formulas for stress and strain is widely used for calculating sections properties for a variety of cross-sectional geometry. For 3D solid Fe, the material constitutive law is the only thing to specify, whereas other elements consideration of modification of materials properties are needed to match the actual structural behavior. Most structural theories are based on homogeneous materials such as steel, although this means structural behavior can be directly calculated using the actual material and section properties. It also indicates that non-homogeneous materials such as reinforced concrete may subject certain limitations. Because of its composite nonlinear performance nature of reinforced concrete, selection properties need to be adjusted for the objective of analysis. For elastic analysis, its strength requirement is the objective. Section properties are less important as long as relative stiffness is correct. Section properties become more critical when structure displacement and deformation are objectives. Since concrete cracks beyond certain deformation, section properties need to be modified for this behavior. In general, if ultimate deformation is expected, then effective stiffness should be the consideration in section properties. It is common to use half value of the moment of inertia for reinforced concrete and full value for pre-stressed concrete members. To replicate a rigid member, behaviors such as cap beams, section properties need to be amplified 100 times to eliminate local vibration problems in dynamic analysis. Nonlinear behavior are most difficult to handle in both complex and simple FA models. When solid elements are used, the constitutive relationship describing material behavior should be utilized. This property should be calibrated by the data obtained from the available test experiments. For beam column type elements, however, it is essential that engineer properly estimates performance of the components either by experiment or theoretical detailed analysis. One member performance is established. A simplified inelastic model can be used to simulate the expected member behavior. Depend on the complication of the member. Bilinear, multilinear also been used extensively. If member degradation needs to be incorporated in the analysis, then take the model may be used. Although the grading model can correlate theoretical behavior with experiment result very well, elastic or plastic bilinear models can give the engineer a good estimate of structural behavior without detailing material property parameters. When a nonlinear analysis is performed, the engineer needs to understand the sensitivity issue raised by such analysis techniques. Without a good understanding of member behavior, it is very easy to fall into the garbage in and garbage out mode of operation. It is essential for the engineer to verify member behavior with known material properties before any production analysis are conducted. For initial design, all material properties should be based on the nominal values. However, it is important to verify design with expected material properties. 12.3.5 Boundary condition. Another key ingredient for the success of the structural analysis is the proper characterization of the boundary condition of the structural system. Conditions of the column or abutments to support or ground points must be examined by engineers and properly implemented into the structural analysis model. This can be accomplished via several means based on different engineering assumptions. So, for example, during most of the static analysis, it is common to use a simple representation of supports, a fixed pin and ruler without characterizations of the soil foundation stiffness. However, for a dynamic analysis, proper representation of the soil foundation system is essential. So figure 12.19 is an example of boundary condition. So we have fixed support, rollers, and pins. General 3D stiffness matrix 6 by 6 members. Usually, most IFI programs will accept a 6 by 6 stiffness matrix input for such system. Other programs require extended 12 by 12 stiffness matrix input describing the relationship between the ground point and the base of the columns. Before using these matrices, it is important that the user investigates the internal workings of the FA program, so the proper results are obtained by the analysis. In some cases, it is necessary to model the foundation soil system with greater detail. Nonlinear modeling of the system can be accomplished via nonlinear spring damper representation, figure 12.20, or in the extreme case by explicit modeling of subsurface element and plasticity-based spring representing surrounding soil mass, figure 12.21. It is important that if this degree of detail is necessary, the structural engineer works very closely with the geotechnical engineers to determine proper properties of the soil springs. As a general rule, it is essential to set up small models of test behavior and check the results via hand calculation. Figure 12.20, it is a nonlinear spring or damper model. And figure 12.21 is a soil structure interaction modeling. 12.3.6 Loads. During engineering design activities, computer models are used to evaluate bridge structures for various service loads such as traffic, wind, thermal, construction, and other service loads. These service loads can be represented by a series static load cases applied to the structural model. Some example of application of the truck loads are presented in figure 12.22 and 12.23. In many cases, especially in high seismic zone, dynamic loads control many bridge design parameters. In this case, it is very important to understand the nature of these loads, as well as the theory that governs the behavior of structural systems subjected to these dynamic loads in the high seismic zones. A multi-mode response spectrum analysis is required to evaluate the dynamic response of the bridge structures. In this case, the response spectrum loading is usually described by the relationship of the structural period versus ground acceleration, or velocity or displacement for a given structural damping. So figure 12.22 is a truck load application example, while figure 12.23 is equivalent truck load calculation example. So 12.4 Summary. In summary, the analysis effort should support the overall design effort by verifying the design and addressing any issues with respect to the efficiency and viability of the design. Before modeling commences, the engineer must define the scope of the problem and ask himself what key results and type of data he is interested in obtaining from his analytical model. With these basic parameters in mind, the engineer can then apply technical knowledge to formulate the simplest, most elegant model to properly represent the structure and provide a range of solutions that are accurate and fundamentally sound. The engineer must bend the demands on the structure by looking at limiting load cases and modifying the structure parameters such as boundary conditions or material properties. Rigorous testing of components, hand calculations, Local modeling and sound engineering judgment must be used to validate the analytical model at all levels. Through a rigorous analytical methodology and proper use of today's analytical tools, structural engineers can gain a better understanding of the behavior of the structure, evaluate the integrity of the structure, and validate and optimize the structural design. That's all. Thank you for listening.